Okay. Should we start? Then, welcome everyone also from my side on the third day. I hope so far you've enjoyed all the talks, all the hands-on lectures and examples. And yeah, I hope you still have some energy now left for a couple of topics at the end. Hopefully they will be rewarding in a sense. And I'll try to cross a couple of fields and give you some intuition on reinforcement learning, how it's applied on a once a daily basis. All of you crossed it at some point. And what's the state of the art there? And what are the things you could look into and what might come next that might be interesting for you? So just a couple of words in the background. So basically just about the research focus, because I'm going to talk about a couple of terms. Have some background in continual learning during my master's. I have some background in software engineering, so you will see a lot of things coming again to programming or coming to neurosymbolic systems if you want so, and in deep reinforcement learning as well during my PhD. And this is also how I concluded my thesis in directions of a bit natural language processing if you want so, or LLMs, but more from the neurosymbolic perspective on LLMs. And this is a bit also where I would say the field is moving a lot in the next couple of years. Founded in the meantime also a company, so this is what I represent today. Also a bit Extensity, we're focusing mostly on neurosymbolic systems for research advancements, so we call it research automation. We're developing tools and frameworks to enable basically, I'll talk about in a couple of seconds, agents, what I mean by that, to autonomously go through literature, propose hypotheses. Actually, I have a slide for that. So you basically can train systems or basically build systems that can search for a lot of index data if you want so, read it, summarize it, collect the information, draft or create hypotheses on top of that, even review it if you want so, and then come up with a final manuscript maybe, or some code base or some whatever your solution is. And this is basically a self-driven bit from some motivation to advance science, because I believe that AI itself is necessary in an exponentially growing complexity of this world to also have a system that can work for exponential growing data. And this led to some case studies, so these are just examples where AI can generate papers. Like this is also before it became more mainstream nowadays, but where you have not only just the text, what you see on the left-hand side, so text-based generation is not I would say the most exciting part here, but it's more about the plots also on the right-hand side, so the code that is actually used, because this is all AI generated, so when, in this case, this is a primality testing problem, the details I won't go into, but the idea is that there are apparently, first of all, the hypothesis was proposed by the AI in circulant matrices, some eigenvalue structures apparently, which allow to determine which is a prime number, which is a composite number. Another AI example is the free body problem, got inspired by the series also, obviously. Just, I always liked physics, so basically thought like maybe this gets also more attention, because people might now associate this also with the series. Here, for instance, like I said, everything is AI generated. So the code, what is actually in the repository, if you look it up, the paper itself, obviously, the text and so on, even the theories and things that it proposes, it's only driven by the human in the idea that we have, I have the intuition, I want to go in this direction, and then basically from there I just correct and try to interfere from as little as possible, and this is about this case studies to just see and push the limits to see where we get. And what you see here, for instance, I don't know, this is a quaternion space, so hyper-complex numbers if you want, so there's apparently some symmetries where collisions can be predicted for a free body problem. If it's true or not, we have some physicists in the room, so maybe they can have a look at it. More practical demos, if you want, so is on material science properties, on using it with tools. So what you see here on the right-hand side is basically a simulation for molecular dynamics. It's based in lamps, so basically the AI can generate code that you can then run on the simulator, and it predicts actually the behavior. If it starts the video, it should predict the behavior of, this is a bit boring. Cool. Thinking. So it basically just predicts the behavior of the sure. QuickTime. I blame it on the tool. So just give me a second to maybe recover from a broken state, or at least kill the tool that causes the problem, because we will have another demo down the line, so it would be nice if it works somehow. So, this is not obviously very annoying. So we have here the simulations, and let's see if we can start it now from scratch. Apparently not. So now it works. You're looking at the wrong one. There you go. So what happens here is basically you have a cryotron. This is a superconductor, which gets cooled usually. This was actually very funny. One of the first in the 1956 and so on, one of the first circuits, if you care about that kind of stuff, that were proposed, so they believed that this could be your computer before the transistors came out, after the tubes thing. And basically, it was just an experiment to show here and demonstrate how the AI can basically generate the necessary code to simulate the heating properties of the rod. And what you basically see then, if we go back to the presentation, that you have different kind of centroids or geometric centroids of the molecules, and depending on different temperatures and so on, they kind of disperse and go apart. So basically, a research automation idea is you have a task, you have propose some instruction if you want, so then you need something that plans. So this is usually your symbolic or LLM-based scheduler. And then you have several tools, as you just saw right now, one of them being lamps, others could be simulators for circuits or for other kind of things, or even just simply retrieval or solvers. And then you have basically some system, specifically that simulator in the mind, that verifies your hypothesis, your theories, and verifies the equations. And then you come up, maybe with some memory system that can store this, accumulates all this information until you start, writing out the manuscript at the end. So this is how you kind of can think about what this term research automation or neurosymbolic AI systems means. And I hope I can convince you at the end that this is a lot related with agents and with RL specifically. Because at the end of the day, if you think about RL, this is literally, you have an algorithm, a model, that in this case is very well defined in a Markov decision process or a MDP. You have incomplete data, as you heard the last couple of days. And you basically have to take an observation, make some internal decisions, place an action, and then basically get some reward for whatever you did in there, and repeat. And the idea is that you're maximizing the objective of following some goal, which can be your set by some preference data. We will talk about that in a second, what that means. So by human preferences or by machine verifiable systems like simulators and so on. And the idea is that by optimizing this loop, you will hopefully achieve a better solution at the end of the day. than you had before. And I want to emphasize this also a bit. LLMs are not agents per se. This term gets thrown around in the industry so many times nowadays, especially where people just assume everything is an agent nowadays somehow. Actually, if you just prompt an LLM, even if it uses a tool, you're actually just instructing a model. You're the agent. You have the goal, because the agent itself, the LLM, has no goal, has no purpose, has no reward, or no basically feedback loop. So, you know, just to really, next time maybe if you hear someone just saying it to everything it's an agent, then maybe correct them a bit, because this was really, for some time, very annoying for me, specifically coming from the RL background. This is a real agent, so Codex probably you know. If you don't know, then you should look into it. It's a very interesting one. It's from OpenAI. And this is your magic instructions, what I put there. Codex came out with this GPT-5 models recently, and there was a lot of backlash from the industry when they started, you know, the first experiments with GPT-5. There were two reasons for that. So when they used the chat interface, basically, they said this is awful, this is worse than the previous model in many cases. That was just because of a programmatic bug. They have this auto modus, if you don't know. They're basically the instant modes, and there's the thinking models and other models. And they have this auto mode, which have an auto router, and they had a bug in the auto router, and basically that bug caused selecting the wrong models, suboptimal models if you want so, or less performant models, and also a lot of probably prompting and other things, bugs in the background. But also with the Codex models, a lot of people, when you used Windsurf or Cursor or whatever, you had in like a middleware, if you want so. If you use that, you said like, what is this crap, right? Because it doesn't work the way I want it to work. But if you actually just installed Codex and parameterize it like exactly like this, still I do it today, then you will see that this model, this agent, actually is very performant. And it can generate a lot of stuff that you saw earlier. So you saw the simulations, all this kind of stuff you can do with that. So yeah, take it. And the idea is now this agent basically creates entire structures and more basically not just one step and not just has a goal actually. So the goal is a bit self-defined. The goal was also optimized during training to keep consistency and other things, and you can look into it if you're interested. So how do you train such an agent? Well, it boils down to, that's where we're coming to language models, so a lot. Boils down that you have actually at the core, you have the corpus is a pre-trained base model, basic language model. So language models are trained when we talk about base models, this is usually self-supervised learning. So you kind of have a huge data corpus from the internet crawled, and then you just basically randomly mask out positions and try to reconstruct them. So you get your base model. That is roughly how training a language model at the core is. And now it's the most interesting part, and this is why it relates a lot with RL and other things. On top of that, there are different phases and different algorithms will skip phases and so on, but basically you come to a supervised fine-tuning phase. So you might have already a more, like in the first versions when GPT-3 came out, did the first experiments also. That was also where I developed some parts of my thesis. That was actually very exciting because you saw already, you gave it a question and they actually gave in the same sense different kind of questions back. Not what you wanted, because usually we're going to put a question you want to answer, but you kind of saw that there is a pattern that it identifies and understands. And this is why you kind of needed as a follow-up, a supervised fine-tuning phase, because you actually, when you pose the question, you want an answer back. At least this is how humans usually think of. Or you want to really say, complete this series, and then you go on, and so on. But that was not enough. There's some superiority to exactly RL, why we need that in the loop, that we get a strategy how to smartly get back an answer to the user, not just imitate a fixed set of data. So we want to learn a strategy how to basically reply to a user. We want to have a strategy how a Codex agent, for instance, creates the structures of the file system when coding, that it looks at information first before it starts just writing code and duplicates it all over the place. So you want to have this kind of like self-consistency in the system. So there's a strategy to it. And that strategy cannot be easily imitated just by supervision. So you kind of need to have something on top of that. This is exactly what comes on top. Usually as a post-training phase, you have RLHF, DPO, there's several algorithms. We're going to walk through them today. And then you deploy an agent with some more tools on top of that, a lot of hacks and constraints. So there's a lot more to these tools, neurosymbolically speaking, than you actually just see or get basically from the news or from the general mainstream media. Speaking of news and mainstream media, greatest commercial success, I argue, of RL is in the use case of language models. And my question to you would be I would be curious just for statistical purposes. I mean, how many of you use the language model or ChatGPT or so? Probably all hands will always rise in private or in, well, it's not so many hands. So either you're not motivated or, okay, not so many hands, no good. Then you should use some. But my more important question would be how many of you work with a reinforcement learning algorithm in practice? Okay, I would say this is 5, 10%, I don't know. How many of you did now know that reinforcement learning is actually partially or to a great extent responsible for that success of LLMs? Oh, 30% maybe, I don't know, 20 to 30%. Now you know. So in my opinion, the most commercial success you will encounter in of RL in the real world that affects everyone, even your grandmother or whoever uses ChatGPT, is coming from RL. You will not find it in astrophysics and all these other fields might come now, molecular dynamics and all of simulations and so on, but everyone in their house, whoever touched a language model, a chat interface or anything like that, has actually experienced RL at its fullest potential. And that's the reason why I want to talk about this today. And there's some timeline to it, but yeah, we'll try to progressively build this up. So we'll start off with the basic of RL fine-tuning. So what is the objective? What we're trying to maximize? So usually we have some sort of reward model, some verifier if you want, or something that kind of gives us the goal where we're optimizing our algorithm towards. And then usually we do some penalization and regularization. Because if you recall what I said at the beginning, you're training a base model first, right? So you have some sort of like very raw diamond if you want so. And then you start polishing it with supervised fine-tuning data. So to get a bit of notch in the directions you want to get the answers back. And then at the end, you want to find even a better strategy how to really reply. Maybe not be racist and maybe be more helpful when asking scientific questions, or don't calculate in your thought process any numbers because you're really bad at it. So 0. I don't know, there are so many examples on the internet, 0.11 minus, I don't know, and then it gets a wacko number out because it cannot calculate. It just, it's really good at reconstructing information from the training data, but it's really bad at actual logic and other things. So that's where the knowledge is actually stored. There are papers that also show that if you just try RL directly on a very crude building up from scratch or language model if you want so, that's catastrophically bad. So you won't get that. So actually all the world knowledge is by this self-supervision process at the beginning, pushed into the model, compressed into the model, and then you just try with different tricks on top of it to just get out the things you want and suppress the other things you don't want. That's why still sometimes if you break a model, hack a model basically, somehow with prompts and so on, then you basically can get a lot of racist comments out of it or other things, right, that are very wacko. So, because all that is in the model, it knows the internet if you want so, or at least approximation of it. So you want to actually keep as close as possible when you do an updating of this model, basically of this base model, you want to keep as close as possible to the origin, because there is the knowledge. If you go too far off, let's say you stray a huge update rule also on top of it, you destroy the weights and it basically all is lost. It's kind of gone. So you want to kind of regularize, this is the Kubo-Geiber divergence that you see there, with the parameter theta. So if you, I don't know if you can, do you see this? Is there a mouse? Oh, wow. So you want to basically have the new model, pi theta here, as close as possible to a reference model. And this divergence measure just says how much do you diverge in this update. And there's some temperature parameter, beta and so to it. You actually heard or saw a lot of this kind of equation during PPO. That's why we have even this clip loss at the bottom here. So this approximation, the crude approximation of that, or basically the hack implementation of that is the clip loss. This could give you a bit different intuition. So the idea is you have this curve.
Can I interrupt briefly? Yeah. Just one question.
Yeah.
Because extra spaces are pretty huge, right? Because this is in front space time. I'm just curious, other people taking other penalty metrics, for example, Wasserstein metrics or whatever, because divergence pretty much influenced also by the duration of the extra space. Yeah.
So there are, yes, papers that also look into other losses and objectives. Question is always how much you have to compute, to get really the real approximation of that loss then at the end of the day. And that's where the clip loss is still the most preferred one, because you just have ratios of probabilities basically, and you just cut them off. So you don't have to do any kind of analytical or second pass-through, second order optimizations or anything like that. So usually you just use PPO. You will see throughout the entire thing that PPO is the most, so proximal policy optimization is the most preferred way of doing it today. I don't know, maybe there might come something else. But so far, since the introduction of PPO in 2016, 15, help me, correct me? 17? Oh, somewhere around that. It's kind of like dominated all over the place. And is always resurfacing because it's so simple and still effective. Yeah, and this should give you just an intuition of having on one axis the reward that you try to optimize, and the other ones that how far you deviate, and you want to regularize this, that you come closer to this optimal point. So you kind of steer, depending on how you steer the temperature parameter, the slope, you might shoot over to just shifting the policy all the time, or you might basically only optimize or hack the reward, or basically the model tries to bypass actually everything else. It just optimize for that reward, but then you have the problem that you're just focusing on one strategy and you're forgetting again a lot of stuff from the other models. So you kind of want to tune to get to the sweet spot of this optimization. And this is kind of a pseudocode scenario, if you want to see it this way. So you initialize your initial policy, so you have this kind of pi theta, so parameters by theta. Usually at the beginning it's the same as the reference policy, because you start with the reference policy. Then you have the reward model, R phi, and then you basically just, for these time steps, you sample some prompt from some data source, so you collected a lot of prompts. You generate, in this case, k responses. I'll tell you why in a second we do k responses. You then basically have some sort of reward model giving and rewarding these responses. And then you do some advantage estimation basically, or with some generalized advantage estimator if you want so. So you get advantage numbers or function out of it. And then basically you do the KL divergence of these ratios, log ratios, and actually the surrogate as a PPO clipping policy or update, and then you just update the parameters. And you repeat. And usually this is not many update steps, so you're not doing this for, usually you have a relatively large corpora, but there are not so many update steps because, as I said, you want to keep as close as possible to a reference model. This should give you now an illustration, because we're actually entering already this RLHF. So this is reinforcement learning from human feedback, because I just told you there's a reward model. I didn't tell you how that reward model is obtained. So you have your prompt, you basically pass that on to your policy, the policy generates something. So you sample basically from that policy now some responses. But now you kind of need to say what is better, what is worse, and having humans do, writing. That was also the downside of supervised learning approaches. If I give you a prompt, a model basically also generates some response, and now you have to also generate a ground truth to it. And generating or writing a ground truth is really costly, really time intensive. What is cheaper is actually just ranking stuff. Imagine I give you 5 solutions or 4 or whatever, and just look at all of them and then you say, hey, that looks all good, but this is the best one, or that's the worst one. So you might say, so you rank the basic responses. So and that's kind of the point of this reward model that I kind of took for granted on the last slide. The idea is that you have human preferences, so you get basically K responses generated by the model, and the human sits there and basically labels them. Yes?
Can we make like a survey, like who actually responded, which one is the better option, after a organized like prompt output?
You mean on?
We did a voting here in the class who is using it, and everybody is using LLMs. But how many of us actually rated?
Oh, yeah, that's a good point. Thank you. So the question is like if you can make a short survey and see how many really actually replied with thumbs up or down, right, after they get the response. I'll talk in a second on that also, but how many did really actually? How many people, when you get a response, you also have like, I prefer this over that, or you thumbs up or down it or whatever?
When you have two choices to
exactly, in ChatGPT even, right? You will get
over that, you have to take one, but the thumbs up, that's optional, so you don't have to.
Yeah, all of them are optional. I mean, the check one, yes, you have to, because that's why they introduced it.
In 30 years, they were options. Now maybe you don't even have the options.
No, they're still there, but they're more seldom. There's also a downside to just, so there are 2 things now. First of all, for training the base, or this model that you see here, basically in the initial phase, you have to think RLHF is in 2022 or so around. With InstructGPT, there was a paper that basically brought this out. You have to think it this way, they didn't have the user base, right? So ChatGPT took off immediately and then had a huge user base, but that came after. So you had, they curated it with teams, so they had their own teams. This is a bit the criticism that OpenAI gets for having people, I don't know, in Kenya or whatever it was, for really bad conditions, just all the time rating responses of models and so on. So the idea is you kind of generate a lot of stuff. Prior to that, create a huge data set as much as you can, and people are just saying this is over that and so on.
There's a bias that keeps in there.
Of course, that was exactly the starting point where you always had this, I don't know, there were the buzzwords that you immediately, let's delve into whatever, and words that were statistically not so representative beforehand, and then suddenly everyone is facilitating and delving and whatever in their texts and so on. So yeah, that was basically this bias is also for the people that labeled the data and preferred and so on. But the point is now, what you're saying now is a follow-up. Now, obviously, they want more data, because the more data they have, the better. This is actually the moat, in my opinion, what OpenAI has over others, compute and data. Because now they have, obviously, all this huge user base, and even if it's just 1% or whatever people now raise their hands, give a bit of a thumbs up or down on the responses, that's already valuable feedback. But you have to take this with a grain of salt. Because just following, this also was some updates that you saw, just following exactly user preferences might even destroy your model again, because users have a very also biased view on their responses. So all of it is really complicated. I'll just try to give you the concepts right now. So yeah, you have this human preference data. You kind of say positive, negatives, whatever you prefer, or you rank them to each other. And then you train a reward model, and then you basically plug that in. Now the reward model, when you have your training loop, this is pre-trained, right? So you train your model, you have it fixed, now you put it in there, and now you basically generate with this other model that you're trying to optimize samples, and your model starts ranking them, right? And it gives its own feedback loop, and then just optimizes and computes the KL divergence and all this stuff, and then basically follows the objective that I showed you earlier. And this is reinforcement from human feedback, because the human is in the loop for this feedback. Obviously, actually we've held one information from you. There are actually 3 models that you have to train, because if you remember, you have the policy, you have the reward model, but to get an advantage, you need kind of like a value function. So you also have a value function that you actually have to optimize. And things get really messy as soon as you have like more than 2 models. Already 2 models are messy, if you think of GANs and other things. There are generative adversarial networks that you can look into. But as soon as you have even 3 models, and so all hell breaks loose, and it's really hard to optimize that beast, or the beasts. So they're basically going all over the place. You do have reward hacking, and you have to clip things, and you have to restart, and it's really messy. So people obviously thought about it. Can we not skip the entire reward model. I don't want to optimize a reward model, right? And they thought about maybe introducing sort of like what is called here direct preference optimization, because you already have the preference data, right? Can you not just compute a gradient directly from there and just feed it into the, as a training signal into the policy? Now, you can do that, and obviously the benefits of it that people did that. So you compute basically, as you see here, as a quick objective overlook, you kind of have this logistic function over, so you just normalize it, basically. So the expectation of a logistic function, but basically what you're doing here is this weighted, so some temperature again, weighting of the log probabilities of the positive samples minus the log probability of from your current model, basically for a model with parameterized by theta, of the negative samples minus the positive samples with the reference. So if you look at it from that perspective, maybe it's easier to read. So you have basically as a preference pairs that you're putting into your policy, and well, you're putting also for the reference model, and then you have kind of your DPO objective here, and you can actually use exactly the gradient signal and update the weights of the policy, and still have all these advantages of still having these ratios, keeping close to a reference model as a penalty, but now you don't really have to have a separate reward model. Downside of it is it's less expressive than the other thing, because the reward model has a role. It's very strategic. You can figure things out and find nonlinearities and so on, outside of just your data that you have at hand, right? So in this case, you kind of lost capacity, if you want, so because you don't have a reward model anymore. Anyhow, there are other things that look into, so KTO, so this is Kahneman-Tversky optimization or optimizer. We always talked about human preferences. Actually, preference optimization is not how humans really think. If I would tell you, I give you tomorrow with, I don't know, 50% chance 100 euro, or today immediately 40 euro, which one would you pick? Which one would?
Because I like risky investment.
Yes, this is the mathematician approach, is the expectation. So the idea is humans usually prefer, sure, give me money today, why not? Because maybe tomorrow you don't see me, right? Where am I? So 50% chance, right? Tomorrow I'm at home or on vacation, actually. So the point is, what I'm trying to make is humans actually prefer, although it's not optimal, so from a mathematical standpoint, you always have the expectation of, and the expectation would tell you 50 euros. Well, why are you stupid and take 40 euros now? You get an expectation more. But that's not how many lifespans we have. We don't have expectations over multiple rollouts and whatever. So actually we have sometimes risk, and we're kind of risk averse. And we're thinking of like, well, maybe I'll take the safe path instead of robbing the bank for $1 million or so, but then maybe risking to be my entire life in jail. I'll just take the 500,000 for the next 10 years or so, working my, A off. So that's kind of the idea. So this is what actually Kahneman and Tversky basically worked into it. Let's just skip the equations, just to give you the intuition. The idea is that you kind of have this so if you have this steep curve on the loss side, and then it goes like on the positive, it's basically concave on the positive side and convex on the negatives, and you see this asymmetry. That's the important part. So you kind of penalize more on the losses because you don't want to spend. It's really horrible to have a huge loss than having incremental gains. That's the idea behind it. If you want, you will have the slides afterwards. You can dive into the math as deep as you want. Then there is group relative policy optimization, what came also afterwards. So with the paper from DeepSeek Math, they introduced actually something really cool. DeepSeek Math, specifically on math problems, they actually introduced this GRPO approach where instead of having to, again here, you still have to, previously still have to have an advantage function, right? If you remember the RLHF and so on. So instead of having to have an advantage function, reward function, and all this stuff, you actually could also go in directions of computing your advantages directly from your group relative returns, if you want. So what does that mean? In this case, you have to assume that you have some sort of solver, math solver, or something that gives you some sort of reward. So you can program that and be aware RL can exploit that. So how poor you do there, RL will find a way to screw you over. But basically, if you do it well, then you actually get directly from the system. So when you do an equation and you make a proof or whatever, and you manipulate the symbols, and you make some assumption of something that is wrong, then, well, the system will tell you immediately that you've done poorly or good. And then you just take the mu, so what you see here is basically the group average over the standard deviation. So you kind of have the spread. And so you basically just renormalize based on the k samples in this case, and this is how you get your rewards back. And now you use this directly to optimize your model, and you have still, again, as you see always, this pattern would kind of emerge all the time, KL divergence, and then you basically have here this clip loss or the advantages, but in this case with the group relative values or reward values, or returns, sorry. Yeah, so, and this was used for training chain of thought and reasoning models, if you want, so on math problems. As a perspective on top of that, if you think of DeepSeek R1, this is, you know, if you looked at your NVIDIA stocks, maybe we had a dip at some point. This is when they brought this out. They had several innovations, apart from shocking everyone that they can replicate reasoning models and everything very nicely with, I don't know, 5 million something budget, or if true or not. I know it doesn't count in the people, head counts and so on, but it doesn't matter. Still impressive. It's magnitudes off from OpenAI and so on, hundreds to billions of dollars. But apart from that innovation, they also brought into the spectrum the RL from verifiable rewards. So what that means is a general approach, instead of just having your solver, only the math tools basically giving you a reward. For things that you have math tools, you use math tools, obviously, and you get a reward directly. But for things that you don't have tools, like human preference data or other things, you can use DPO and so on, and you can mix and match, basically, these approaches. And then you can really train good chain of thought reasoning models out of that. I personally don't like the name chain of thought, because models don't really think, they just produce statistically multi-step generative processes. But that's a different story. Or maybe a story can, on the next slide, connect. But this is roughly just the outline, again, of the pseudocode. So you basically have your k candidates that you're sampling from. You compute your returns, if you want, so from there, based with this kind of verifier / scores, wherever you get that from. You can even have heuristics and other things doing that. And then you do this kind of normalization, as you saw before. And now you can update your policy with that, which is neat. And is a lot less friction because you have less models to mangle around. Now, yeah, there's also a schematic. So you can see this basically just piping up and then building up. And depending on what kind of, like, at the far right end, which methods, I'll also talk in a second about agro. Basically, you can see this as a pipeline. Symbolica and vertex score, I snuck this in. This is basically from my own publication. This vertex score, what you see up there, and if you're interested in verifiable rewards or general way of having verifiable rewards, the symbolic AI paper, you actually see the vertex score, which is based on the inception, Frechet inception distance. If you know anyone of that, does anyone know that paper? Oh, good. Want to explain it? No. No. So the idea is that you kind of have the Frechet distances between, like, if you want to say a reference distribution and a generated distribution, if you want so, and you try to align these two distributions with multivariate Gaussians and whatever. There's some technicalities to it, but what it boils down to in the paper that I've published is that you can actually have kernel functions as an approximator for that. So you can have any kind of kernel that you can build. This is this maximum mean discrepancy, what you see here. And there's just some normalization to it. So it's a Z-score normalization. Doesn't really matter now for the point that I'm making. But what you see here, the integral, is basically what you're doing actually. You're integrating over time steps, or if you think of reasoning chains, right? So multiple steps. And what you can do here, this is the most general way of how you can do this. Whatever you can fit into a 0 and 1 range, so being a heuristic, being obviously something what is coming from a kernel, or something that comes basically from some solver, can be integrated in there, and you actually can have the most general reward function if you want to build it with this scoring. So that's what vertex score. It's actually a metric, but as an approximation, it's the score, what you see here. And you can obviously combine this with GRPO and other things. And I had this question yesterday. I don't know where the person is now. Ah, there he is, thank you. I just snuck in this slide as well. There's design by contract paper that followed up on our framework. And the question was in the directions of how can we ensure that when LLMs, for instance, produce now this kind of like fluent text, if you want, so for planning. So the idea was that you have this scheduling of a plan, and then you have to execute on the plan, right? But all of it just text usually. Is there a way to make this more robust, verifiable, etc.? And there is. And we built basically a sort of a library for that. It follows design principles from software engineering, design by contract, such that you have a contract where you say whatever the precondition is before executing the actual whatever you're executing on it, and you have a post condition. So what you have is like it basically is a decorator. That's what you see here on the right-hand side. That's why I want to just boil it down to the most simple thing. You have a decorator of just conditions that you approach, and the LLM will basically just be guided through those conditions and self-prompted, corrected, everything happens automatically. And then you can ensure that whatever type comes out as a triplet, in this case was an example from creating an ontology and creating sort of graphs, knowledge graphs. You can, for instance, build up type-safe structures and objects from LLMs in the loop. And you don't have to have a lot of metacode because all of it is behind this library and things. So you kind of have this, what you see here, gamma is basically just is subject to, or basically says that X is subject to this type tau. Anyhow. Then we have basically self-rewarding language models. There are approaches, obviously, how can we get this reward, right? We want to have scalable systems. We don't want to have humans in the loop all the time having to label it. And there are approaches where show that they also use an LLM to basically rank an LLM. So you can have scores saying like this is preferred over that. I wouldn't recommend you to use numbers. I would recommend you to have categories. And you just omit the ties, because you don't care about the ties, but you care about the extremes, so positives and negatives. And then you actually use an LLM as a judge in the loop to blow up your data set. This works to some extent. It's like data augmentation, if you want to see it this way. So obviously it implies that your model has to be to some degree already good. But if you think about GPT-5, sorry, yeah?
Yeah, but for the LLM judge, I believe to have read that you can, by designing certain or implementing certain words in your command, that you can sort of make the LLM output 95%.
Yes.
Only wrong answers.
You inherit all the negatives of it as well. So you basically, what you're talking about is roughly, so the question, in a way, question or the comment is, you basically can just say to the model, give me 95% of whatever, this is a super solution or whatever you write in there, and suddenly it biases the model to be, yeah, that's a super solution, you're right, cool. But that's not true then, right? Yes, you inherit all these problems with it, right? So the idea is you have to have a robust model already from the start in a way that is kind of, but you will always reward hack it somehow, right? So, or reward, not reward, but in this case prompt hack it. So you can always like prompt engineer something and then drift it off. But it's like, that's why I said it's like a data augmentation algorithm, you can see it like that, or approach, where you can artificially boost it a bit, but you have to be aware of exactly these kind of things can also happen, that your model actually biases itself. There's actually a slide later on that I can show, which is very interesting. Yeah, so the main takeaway here is you just use an LLM as a judge, for these candidates and for rewarding, and then you use that data set for training again. Then there's basically self-play theorem, self-play with theorem provers basically. So what also came out, and this is actually very cool because now you have models that, especially in this loop with math, so that's the direction why actually this more recent models from OpenAI and also from Google were so successful at I forgot the competition. Math Olympia, thank you. Because basically they trained it in this loop. So they have like models proposing a conjecture, then they have the model prove again the conjecture, and then they can use a verifier to give reward signal back. So they use a solver and so on, and they can really say they close the loop basically by just having models propose a lot of problems and then trying to prove them and then trying to verify them with a tool, and in math and in programming and other things. So that's also why Codex works so good in a certain degree, because you have unit tests and you can basically kind of close this loop, and it's in a way self-play mechanism. And now the model can just optimize until it converges to some optimal state if you want. So, and then you just remove all the syntactic sugar if you want, so, and just use the raw model, and suddenly it's so good as Olympia math contestants. Can take a look at that. I mentioned quickly agro, any generation reward optimization. I think for an interest of time, I'll skip the details of the math, but the point is, because you heard these days on and off policy optimization, this paper tries to combine both. So you want to have on and off policy data into one coherent optimization framework, and you can switch between whatever data you have. And it's about, the main idea behind it is just to have sort of figured out a way to importance weight the on and the off policy samples if you want, so in a smart way. So you can look also at the math and at the paper to get more details if you care about that. Yeah. So just as an overview, because we saw a lot of algorithms, a lot of formulas thrown at you, trying to structure everything into a table. So you have basically your RLHF, starting off with just PPO if you want so, has a reward model, a verifier is optional, you can always still use that if you want, but the main idea was the humans were the verifiers. And it's on policy, and then we looked at DPO, direct preference optimization, which tried to omit all of these things to just directly push the gradients on the model, has some limitations with respect to expressiveness and complexity. There's ORPO, which I didn't include now, but you can also look into that if you're interested, but it's on the same. There are several models that look at more than just preference data, so trying to get more of this prospect theory and other approaches, how to measure which one is better than the other, which reward is more representative of what we humans care about. Then basically GRPO with the DeepSeek math paper and so on, with RLVR following up with DeepSeek R1 if you want so, that uses actual verifiers, uses its own policy and doesn't require reward models anymore. And then trying a different algorithm that basically tries to bridge on and off policy into one coherent framework, agro, and you can leverage all the data. Because remember, on policy methods have to throw away their data because you basically are optimizing for a different gradient. If your model keeps shifting and changing, and you would use the old data, and because you need the log probabilities and so on, you're optimizing the wrong thing. So this basically just corrects for that shift. Here are also the references, and at the end there are a list of references. Maybe beyond preference, optimization, or rewards, what you saw this way, there's also things that you can look into, because this is a bit what I'm trying to now open up. It's more on just to give you more ideas and more perspectives on what to look into. Reward shaping, for instance. Be aware, reward shaping is sort of like, you can always hack something into your reward to make it somehow work. You usually want to have a reward shaping when you have like long episodes, for instance, long horizon problems, and maybe even sparse rewards. So meaning that you have at the end, you play the entire Atari suite or a game, and then at the end of Montessori or return or whatever, you get a reward. Congratulations, you made it. Well, if you just would have to wait for that reward signal to optimize for, then you will probably never find anything because there are way too many possibilities how to screw up and die. So the idea is actually you're trying to bring in dense rewards as close as possible to key events. So you try to pull back, if you want to. And if you don't just reward shape it, so this is a key that's important, and this is important, and you just stick rewards on it, what can happen is you might screw up the optimal policy because you're basically shaping something into which is diverging from the actual policy that might be optimal. There is potential-based reward shaping, which kind of corrects for that and still preserves optimality. There are other methods like rudder, coming also for JKU. It's basically reward decomposition, which kind of uses LSTMs or other methods basically to pull back the reward on key events, and then they basically redistribute the reward. So you have at the end 1 or 0, but they actually redistribute to key events because of some feature extractors that capture signals in delta states and so on from the LSTM states and so on. But look into it if you're interested, because there's a lot of detail and depth to it. And there's obviously trust region constraint update methods or constraint policy optimization methods that can also be of interest for you as with proximal penalty. This is what I said earlier. There's an interesting paper looking also this random effects or weird things, spurious rewards, for instance, and rethinking how we train RLVR, because there is apparently this phenomenon with the Quen models that you can just give them random signal back. So you basically, even if it's the wrong label or whatever, you just give them a signal and you optimize them and then suddenly they improve, which is weird. Like, how does that work? I haven't figured it out yet how it works. I'm still digging myself into understanding what the hell that means actually. If you're smarter than me, take a look at it, or take a look at it anyways, but maybe you can tell me what to make out of it. So if you're just flipping a coin and just giving reward back to these models, it improves. The idea or the intuition is that apparently everything is already in there in the model, like I said earlier. The information is already in the model with the pre-training and base models and everything. And it's only about you need some sort of like signal to emphasize those states and to basically just push them into the distribution. And actually you're generating anyways a chain of thought if you want, so whatever you're generating. So you already have a bias in there. So if you want to give my intuition, this is my intuition of it, but I don't get it, read the paper and maybe you get it better, why this works. Then there's goal conditioned and reward-free reinforcement learning. This is what I, in the first day, asked Sergey in an indirect way, because this is very interesting for what if you cannot model the reward in a smart way, because you always had like either humans or verifiers, like solvers and other things doing that, but what if it's just pixel-based, for instance, and so on, right? You just give you images and so on. Sure, you could say this is, but like looking at two different pictures just shifted a bit, which one is preferable? You don't know. But what you know is, as humans usually also know, we kind of have, if I want to go for coffee, I have now, in my mind, I know exactly how the coffee looks like, the place in the back of the podium. And then I can just, condition myself on that, and that's my goal. And now I just wander around like a random agent through these halls and so on until I kind of like approximate that state. And then like, hey, that's where I want to go. So you basically what you're doing is in your Q function, you're not having only states and actions to estimate the state action value, but you actually also have a goal state. So you kind of goal condition where you want to go next. And you want to try to get as close as possible to that. And there are also some cool tricks like hindsight experience replay, the paper, that you can even use the negatives of it, the sample. So meaning that even if you end up in a different state at the end, which simulates a different path, you use then that as a positive for that path, which is really cool, because then you say, okay, we can reuse, even if you just wandered randomly around, still ended up in a different goal, then you use that and say like, hey, congratulations, you have hindsight information now to update your policy. Very interesting paper, so look into them. Yeah, talked about chain of thought, and so my thoughts on chain of thought is there is no thought in LLMs. It's just statistics on a hierarchical basis. They do not do deductive reasoning, but anyhow, this is a longer discussion if you want to take it on. Actually there is basically on the token level, you can also put attribution of rewards and update those, but yeah, I think this is overkill a bit. The more overkill is even multi-agent RL and meta-RL. So if you're really desperate, that's where you usually start meta-learning. Because you don't know what to do, but you know they have a lot of problems, and you might start meta-optimizing something. This is how I always avoid meta-learning, because usually if you don't know how to model your rewards and your problem and everything, but then just go meta level on top of it, is just making everything more fuzzy, and you don't know what you're actually doing. RL squared, so RL in RL. So, but the main idea is you have this kind of like inner outer loop. So you have basically like an LSTM usually, keeping trace, if you want, so of the previous environments and states, and then you just basically update your inner loop with these different environments that you're exploring all at once. The hope is that you get better initializations states. My recommendation is look into it if you're experienced. For instance, I know for a fact that Simon is very experienced. He did that and that works. But if you're not, then this is the last resort you should go at. Because you should understand everything else before you go meta-learning. And multi-agent is also hell, because usually there's a hack to it, which I don't like. Multi-agent systems are actually built the way that they're always a global value function or state action value function, because all agents are sharing that objective somehow, because there's some collaborative objective, right? That's actually not how in real world scenarios that works, because we're not having some collective mind where we're sharing our values. So it's just a way of trying to synchronize the system, in my opinion. And I haven't really seen so far any paper that convinced me that really managed to decouple all the agents independently and then find a way of over a bottleneck to synchronize them. Maybe the hopes of language models could be, again, because they have a common basis of the same world model, if you want to see it this way. So they have the same basis, so they could now start collaborating. There are some papers now actually that looked into this small town, I forgot what it was called, this kind of simulations of little towns and so on and whatever, and every agent has its own role.
You think there would be some LLM-based Keynotes in the end?
Yeah, it will for sure be. Because you need a base world model, right, to understand, because in all the other, before LLMs, this was literally how do you communicate between agents. That's the problem. Right?
It would be interesting just to mention credit assignment here, because if you have multi-agent problems, for example, like football day, for example, football, whatever it's called, and you have one guy only hitting the goal, and the other one is just running circles, right? And the reward is you got a goal, so teams up. So the other one is just inferring that it's a good idea to run just in circles. That's the problem, right? Usually. So that was really hard to do this credit assignment for each entity in the multi-system.
Yes, maybe also for the audience. So yes, exactly, it's a credit assignment problem because you have different agents. One could just randomly stroll around and the other one shoots a goal. You have also correlations now suddenly, and then it happens that the one has to always run around because he got positive feedback, right? Because now we shot the goal by chance. And there are issues how they communicate to each other. So that's and how do you assign credit to how they should collaborate usually in the tasks. Especially one has to pick up a key, or another one has to open a door, and somehow they have to do it in different places at the same time. That's very unlikely that it happens. Usually it's circumvented by having this kind of global value function, if you want, so that kind of shares the state or the state assumptions of it. But that's not really collaborative, multi-agent in my opinion. It's just more action spaces, if you want, so from a different perspective. That's how I would see it. There's several other topics you can also look into. A lot of things moving forward now are in robotics, are also in multimodality, so vision language action models. So really trying to get multimodal also on the RL side, and also one of the holy grail is to try to get the general purpose policy or general purpose RL algorithm. that you just train on one of all the simulations and games, whatever you had, and then can you easily just plug it into a new game or whatever, and then it just knows exactly what to do because it kind of shares the experiences and learns. Offline RL and other things in diffusion models, you heard it also from Sergey on the first keynote speech. And there are even RL, so everything you can think about RL can pair with something, so evolutionary strategies and methods and so on, and there are a lot of ways to explore the spaces around you. Yeah, maybe closing it up with best practices. Already, I think, over time a bit. Or am I? Sorry. So best practices in RL, so going beyond LLMs and so on, for researchers, try to pick a niche problem, try to basically pick the problems where I said, like, I don't know what's happening there, right? So that's maybe a good start. And then basically try to incrementally address that. Don't go overboard nowadays, especially with a lot of computer requirements. Maybe don't go on your first problem on a language model. That's usually costly in compute. But yeah, for practitioners, try everything else before trying RL. so usually people come around and like say, oh, I tried RL, it doesn't work. And so did you try, I don't know, you try was per problem. There are a lot of heuristics and other approaches that already, or evolutionary strategies that already approximate that problem so well. Why bother? So if you tried everything else and you're stuck and you need a strategy, so you need something that thinks in a strategic way, if you want to call it thinking, then you probably are in the realm of RL. Beforehand, you should have all the algorithms explored because they're highly optimized. And you will lose a lot of time and effort, and your C-levels will be really, really annoyed with you not delivering anything. But for research, it's still interesting. Yeah. Sure. There are other things. Try to guardrail your problem. Try to always make it, some way guided and so on. The more you can cut down the search space. One part of why RL fine-tuning works so well is also because you already cut down the problem to a narrowed search space now, because now your language-based model, your base language model is already very well at producing tokens, if you want so, right, real words. And now you actually cut it down from all possibilities and combinations to, very specific strategic ways how you align the tokens and the words, right? So this is basically what I mean by guided or guardrailing the problem. Yeah, you can take a fast tour on robotics if you want, but I think we'll skip it due to the interest of time. Yeah, we're looking at a lot of algorithms today. Hope it was exciting. Try to bridge it a bit with neurosymbolic systems and LLMs, where RL actually fits in perfectly, in my opinion. You will see a lot of things in this direction moving forward, especially with simulators and a lot of sciences, material science, other things popping into existence and expanding the toolkit for you to play around. And yeah, closing it up, I have basically also some Discord channel if you care about connecting with others that have basically collected in there, 400 something people. If you want, feel free to join in. And maybe you're more active than I am, so lately a bit caught up in business. And I want to show you and close with the notes of we had shooting up some robot, right, our little Wally on Mars, if you remember from the previous lectures, also from Catherine and so on. And I was thinking maybe this is just nice to close it up. What could Wally do on Mars and look at? And basically, I worked on some new publication now, basically on black holes, also generated by AI. Could you please just close this? So, and what you see here is, again, a great tool. This is really an amazing tool, I would say. QuickTime is dying. So, can I please just show this one last example? So basically, Wally could just sit on, what are you doing? Well, apparently no video for you today. Oh, no, here it is. So, Wally could just watch out and gaze into the dark night sky with a better look from Mars. at black holes is a simulation built by AI agents. Oh God, this is horrible for you to look at. Sorry, you can watch it in the video live stream if you want to see nice curvatures. And this is the ring down tone basically. So if you care about black holes, when they merge, they kind of have like this bell sounding. If you transpose it from the gravitational wave from the spectrogram into the real sound, this would be how it might sound. Not so spectacular, but it's cool. All built by agents. Last comment, all the slides that you just saw today, also built by AI. So it literally all is AI generated, what you saw today. Take that as you want. So yeah, thank you very much. Questions? Oh, sorry, yeah. Should I give you a mic? I wish.
So I was wondering if you could go back to the first slides you showed, so the examples. Did you compare the AI solutions to...
Which one, like literally at the beginning?
I mean, yeah, for the
Okay.
free body problems and so forth.
Ah, okay, this one.
Those ones, yeah. Did you compare, so did you check those solutions then, what the AI did with...
Well, so what I did here in all the papers, there's also the black holes, so ring down bounds, etc. on ultraviolet regularized black holes, of course, are always symbolically verified at least. So I'm not a physicist, so I'll give you that disclaimer from the beginning. Although Hitten got the physics Nobel Prize, maybe I am, I don't know. No, just kidding. They have been basically verified with symbolic solvers. So they generated, so the same approach as you saw earlier, with RLVR and so on. So you kind of have at least solvers that you know that the derivations are okay. If the assumptions are correct, that's a different story. So for that, you would need experts to say, okay, because the assumptions comes from the human a bit intuition, they want to prompt it, go in this direction, do that. They're really bad at trying to derive themselves assumptions and things because they don't understand the world really, the physical world and so on. So LLMs have some limitations still everywhere. Material sciences and physical problems and other things. So the assumption mostly comes from humans, the intuition comes from the human to go in this direction, but everything else is, as far as possible, generated and verified.
So you check it like with something like Lean, so proof assistant?
Yes. SymPy, Lean, things like that, yeah, exactly. But for instance, you can have definitions, and the definition is just wrong. Yeah. So it's basically now the question is semantically, what does that mean, right? So, exactly. Any other questions? Yes?
Maybe you can just forward it.
Yeah, sure.
You have this table with different methods to improve LLMs.
Yeah?
And on one you mentioned that it's very compute heavy. Isn't the compute bottleneck anyway on LLM inference to generate data to apply reinforcement learning, or is the method itself the compute heavy task?
Yeah, I mean, when you optimize, that's the compute heavy task nowadays. I mean, you can have on my this is M3. I can with 128 gigabytes Apple Silicon chip. I have a 70 billion parameter model easily on it. I can do inference with it. It's probably not so fast as the are in the cloud, but that's not the problem in my opinion. The problem is if I start optimizing, then everything breaks. So, yeah. Any other questions? And there are, by the way, from Microsoft also recently a 1-bit optimized language model that increased tokens on even on CPU optimized. So there are a lot of things, and if you look into Llama CPP and other things, they basically nail it down for inference at least tasks on edge devices. Yes?
I have one more on, recently there was a shocking paper I read, which basically said that if you optimize for certain metrics, that you would actually enhance hallucinations in LLMs.
Sure.
The current metrics that they use force hallucinations to go up. So I was wondering if you were aware of other metrics or other issues that, or how to
this is like, in my opinion, it depends a bit on what you're optimizing. Like, is it like a reward hack that the model discovers, and then or exploits? Let's say this way, something that you didn't plan beforehand, and then just like I said earlier, all kind like weird things happen, like the RLVR, where you have suddenly a model improving, although you give it wrong rewards and wrong labels and signal, and just it somehow improves. I don't know why. I think this, because the problem space is so huge, you have all these kind of effects. Hallucination, in my opinion, is anyways, like, I mean, you have a generative model, you have incomplete information. The question is now how you design your reward, basically, or your policies and reward models around that is shaping the space of how you recompose the fillings in what is missing, right? You can do it a bit wrong. That's why I think there were things talking about, literally about using just human demonstrations, like after the rollout of ChatGPT, for instance, there were a lot of issues in exactly this direction, because if you you're not aware of like what humans really prefer, they might even bring into wrong information, right? Because especially this, people all complained when GPT-5 came out that they're not so, what is the word again in English word I forgot, suffocant or whatever the word is. The idea is that it's not, emphasizing their responses as they was like, yeah, you're right, you're great, and whatever. But that's because that was the bias of 4.1 and all the other models before, to, kind of push the user to engage it more into the system. Now people just got this dry response from GPT-5, and they feel like it doesn't support me anymore the way they prefer the other model. Now, is this the right way? No, it's not. The objective is actually wrong, emphasizes even wrong biases.
I think there was also a fun case where, I think it was Croatian, where the Croatian-speaking people downrated the model so bad that they didn't want to speak Croatian anymore.
Yeah, so there are all these kind of effects. So but it plays a role why you should pre-filter and be very careful what you bring into your optimization, because the RL will find a way to exploit that. That's always the case. That's why I'm saying reward shaping, other things, I really have to be careful with that, because RL will always exploit it. And then you get a model, but whatever you get is the question. Yes. Where? Okay. The last question left, good. Then thank you again for listening. Sorry for being a bit late. So, for the online audience, or are we're closing it. Thank you very much for participating, and hope to see you next year.